Hello everyone, myself Chandrasekhar Maurya, and here I am going to present the presentation on topic experimental investigation of rheological property of water-based carbon iron MR fluid. And this is my outlines, introduction, application, result, and discussion. And in result discussion, there is a characterization of MR fluid, rheological measurement, creep and record behavior, conclusion, and references. First, Rabinov in 1940 proposed the concept of MR fluid, and this MR fluid is the suspension of the magnetically soft micron-sized particle dispersed into the magnetic carrier fluid like mineral oil, water, and synthetic oil. And this MR fluid shows a reversible and speed transition from liquid to solid effect under the applied magnetic field. As we can see in figure 1 that when there is no magnetic field H is equal to 0, thus magnetic particles are distributed randomly, and when applied magnetic field in a particular direction, this all the magnetic particles form a chain structure along that direction, and because of that the suspension of this the viscosity of the suspension increases. Now, the summer flood of low power needs a broad temperature stability and eliminate the instability of devices. The MAP flood have excellent ability to integrate the silent, fast, and continuously adjustable mechanical property and rapid response and enhance them with electronic control unit. And this MR effect affected by the size, volume of fraction, type, and shape of the particles, physical property of carrier fluid, intensity, and direction of magnetic field. Also, the mode of operation. This water MR fluid have a higher shear stress and higher than the hydrocarbon MR fluid under same conditions. Now there is some application of water-based MR fluid mainly used in the dampers and medical devices because of their instability with temperature. And this MR fluid is in the fluid suspension, a seismic temper test, and this is the figure for which presents the commercial linear MR fluid based damper proposed by the Lord Corporation. This is the coil which produce the magnetic field, and this is the MR zone. And the MR also used in the MR fencing processes where this is the carrier wheel, and this is the magnet which produce the magnetic field over the fencing zone, and there is the MR fluid delivery. Now, MR fluid delivery. And now, when you apply the magnetic field, these magnetic particles form a chain structure, and when they will rotates the magnetic particle, and there is some addition of such abrasive particle. When they rotate, when they flow, the irregularity of the surface is removed by that abrasive and magnetic particles. And now this magnetic MR fluid also in the medical application for the knee prosthesis applications. Now the here I am prepare MR fluid by the suspending the flex carbon iron in water and adding the bentonite as additives. And we found that we are adding the additives, a small clay layer form over the carbon iron surfaces, and also the bentonite nanoparticles fill the voids between the micron size carbon iron particles, which enhances the rheological property of the MR fluid. And figure D is showing the schematic diagram of the suspension. Here there is no magnetic field. All the particles, carbon iron and bentonite are distributed randomly, and we applied a magnetic field. These bentonite particles fill the voids between the magnetic particles, and this magnetic particle also form a chain structure along the direction of applied magnetic field. And we measured the magnetic property of the suspension. We found that pure carbon iron had the higher magnetic saturation than the addition of the bentonite, because bentonite reduces the magnetic saturation because of the non-magnetic property, non-magnetic materials. And also we have observed the ADS analysis to observe the existence of the bentonite. We've seen that when there is no addition of the bentonite, pure carbon iron, there is no aluminum silicon, and weight percentage of Fe is higher than 0.91.41. When we adding the bentonite, there is the existence of aluminum and silicon, and also the reduces the weight percentage of Fe. We have performed some rheological experiment like shear flow mode. In shear flow mode, we have observed that the viscosity is decreasing with the applied shear rate for 0 to 100, and which showing the shear thinning behavior. And similarly, we observe the shear stress versus shear rate behavior, and see that, and the shear stress showing the constant relative to the shear stress of shear rate of 100, And we observe that adding the bentonite 1, 2, 3, 6, the shear stress and viscosity only increases up to the 3 weight percentage of the bentonite. And after adding that bentonite, the reduction of the rheological property like viscosity and shear stress, and it is happening because adding the more non-additive non-magnetic particle reduces the MR effect of the suspension. And also you have observed that in increasing the magnetic field from 0 Tesla to 0.676 Tesla, the value of viscosity and shear stress increases. And we can clearly observe in the figure uh, of static electric or magnetic field. In figure C, we can see that as the magnetic field increases, the static electric increases up to the critical strain, and after the critical strain, the magnetic particles start saturating, and the static electric decreases. And also we can observe that adding the weight percentage of bentonite 1, 2, 3, 6%, there is the enhancement of the static yield state. While the higher magnetic field region, there is a small static yield state for the 6 weight percentage, because at higher magnetic field there is a domination of the uh, magnetic field, because this higher weight percentage of additive reduces the magnetic effect of the suspensions. And in 1986, Ginder also proposed a equation that this tau y statistical effect directly proposed related to the H square H magnetic field, where when this applied magnetic field is below the critical strength, this tau y is proportional to the H power 2. And there H is the magnetic field, phi the volume fraction of suspension, and mu naught is the permeability of free space. And now when this applied magnetic field is greater than the Hc and lower than the complete saturation of the magnetic field, that T tau y illustrates is directly proportional to the H power 3 by 2. And now a situation comes when the particles are completely saturated. In that condition, the T tau y is independent upon the H, but independent upon the local saturation or rotation of the magnetic field. This is the mu naught and ms. Now we observe the effect of the bentonite over the static elevation. We found that up to 3 weight percentage of the bentonite, there is an increment of the static elevation. After that, due to the large amount of the non-magnetic additives, the static elevation decreases. And this large amount non-additive magnetics reduces the effect of the magnetic effect. And you can clearly in the figure table, in the table 1, we can see that in the low magnetic field region 38 67 applied magnetic field strength, there is a higher value of yield stress for the 6 weight percentage. And while in the case of higher magnetic, the 3 weight percentage higher yield stress is happening because at low magnetic field stress, no magnetic field, this viscosity support the magnetic chain structure, and that dominate the MR effect. While in a higher magnetic field region, the MR effect dominate the viscosity, and this higher amount of clay or bentonite particle reduces the chain effect of chain structure. So that's why there is a weak chain structure, magnetic chain structure at higher magnetic field for the 6 weight percentage of the bentonite. Now we perform the some amplitude sweep to see the effect of shear strain over the G and G double S. You observe that approximately 0.1 strain percent with strain, there is a constant plateau of the G dash storage modulus, and which is independent upon the applied strain for that region. I mean, when we increase the value of strain 0.1 to 100, we can see that the G dash and G double dash will start decreasing, and a point comes where G double dash is loss modulus greater than the G dash storage modulus. At that point is called crossover point, and crossover point there is a plastic flow of fluid occurs. And also we can see in such figure that the shear stress versus strain, and we can see that as we increasing the value of strain, the shear stress is increasing with the applied strain. And we also observe the magnetic field versus G max, G dash max, and G double dash max maximum value, and we see that as we increasing the magnetic field, the G double dash and G dash is increases and then start saturating, and it's happening because of the magnetic saturation of the particle. And in figure 11 also we can observe that at higher magnetic field region, there is a very small difference between the G dash value. Now we perform the frequency shift, where we apply the frequency from 1 to 100 and observe the value of stress and G double dash. We can see that the G dash is showing the almost constant plateau over the applied frequency, and this behavior so a solid like structure of the fluid. And also the shear stress is constant throughout the applied frequency, and this constant shear stress also showing that there is no deformation or the flow of occurs of the fluid under the applied strain. And we also observe the G and G double dash under the magnetosweep and see that with applying the magnetic field, there is an increment of the both G and G double dash with the magnetic field. And initially at lower magnetic field, there is a increment slope is higher, and at higher magnetic field, this is slope is decreases because of the magnetic saturation of the particles. Now we perform a deep recovery behavior to see the microstructure behavior of the suspension magnetic particles under the constant loading. And this is the schematic diagram which show that there is a gamma IC, which is the instantaneous creep strain, is the summation of the gamma E and gamma P, and this the gamma are reversible retardatory strain, and gamma V is the viscous strain. And after in the recovery phase, there is the gamma IR is instantaneous reversible strain, which is equal to the gamma elastic. And then there is a gamma R retardatory strain, and this is the irreversible strain after in the recovery phase, which is the summation of the gamma P and gamma P. And this plot is showing for the non-linear viscoelastic materials. I mean, there is a linear viscoelastic material. This strain will instantaneous strain will be completely reversible in the recovery phase, and this case this the gamma P is equal to will be 0. Now, so this is the plots. We have performed the creep and recovery behavior in two cases. We by applying the different constant load, and in second case, figure 7, we applied a constant magnetic field. We applied constant load and changing the magnetic field, and now we can see figure 16 that when the applied magnetic field 200 pascal or a constant magnetic field 0.35 Tesla, there is a instantaneous strain, and then the strain increasing, and there is a creep phase. And in recovery phase, when we remove the load, we can see that there is a complete recovery of the strain. This plot shows the linear viscoelastic behavior of materials. While we increase the value of applied constant strain, constant stress is 1500 Pascal at 0.35 Tesla, we can see that instantaneous strain occur, but there is not a complete recovery of the strain under the recovery phase. And this is so the nonlinear viscoelastic behavior of material. From here, we can observe that when the applied magnetic on the applied constant stress level is higher or more than the dynamic yield stress, the flow of the fluid occurs, and the rupture of the magnetic chain structure, and that will not recover in the recovery phase with time. And figure 70 so the influence of magnetic field, where you can clearly see when increasing the magnetic field from 0.1 Tesla to 0.54 Tesla, the value of the strain is decreasing. Must the fluid so a stiff solid like behavior. Now these are the conclusions. You can observe that the so the bentonite enhance the rheological property, and MR55 with 38% of the higher stress of 29.50 kilopascal at 0.76 Tesla. And we also observe through the amplitude shift test that for the 0.1 percent of a strain, that is critical strain, the storage modulus is showing the constant plateau, and the storage modulus gives the static plateau area entire input angular frequency under the frequency shift, and sacrifice the well-known Fedlock behavior and the creep and recovery behavior instigation of mass suspension suggests that the instantaneous creep strain contribute and the recovery strain are highly dependent upon the applied constant stress level and magnetic field. Now the instantaneous strain contribution increases in the creep phase, while recovery strain reduces with increasing the constant stress level at the applied magnetic field. And we have also observed that instantaneous strain decreases with increasing the magnetic flux density at constant stress level because MR suspension becomes stitched under the applied magnetic field. Now these are the references, and thank you.